Um, so in order to find the thrust profile for our rocket, we first needed to come up with a set of equations that essentially solved for the change of velocity in the rocket over time in terms of different parameters. So the first equation that we knew from fluid dynamics was that thrust is equal to the nozzle velocity times the mass flow. Now, something that we assumed was that it was an adiabatic process, therefore there was no heat interaction with the environment. So we could just say that PV to the K equals P naught V naught K, where P naught is the initial pressure inside the bottle and V naught is the initial volume in the bottle itself. And of course, since this is an adiabatic process, K is 1.4. From there, from Bernoulli's equation, we saw that, P minus PA equals 1/2 rho times nozzle velocity squared. There were some other components, such as the velocity of the fluid at the surface, but we deemed these to be negligible due to the velocity just being zero. From there, we were able to essentially so additionally, we also knew another relation for mass flow, which is just rho times A times nozzle velocity. Rho being the density of water and A being the cross-sectional area of the nozzle itself. From there, we can replace that into equation 1, and we get that the thrust is equal to nozzle velocity squared times density times the cross-sectional area A. From equation 5, we can substitute it into equation 3 and get a relation between the pressures. So P minus PA will essentially be the gauge pressure from the bike pump. So we have P minus PA is equal to thrust over 2 times the cross-sectional area of A. From there, you can get like a general equation for thrust, just knowing the pressure differences. So T equals 2 times P minus PA times cross-sectional area A. So then from there, what we did was that in equation A, we essentially said that we rearranged, we made some substitutions in what's called this equation, right? In equation 3. So we said that P is equal to P naught V naught over V to the K minus PA is equal to the 1/2 rho nozzle velocity squared. And then from there, since we wanted to find the change of the nozzle velocity in respect to time, we took the time derivative, and we got negative K times P naught times V naught K times V to negative K minus 1 dV dt, because we differentiated the volume, because that is also changing over time, is equal to rho times nozzle velocity times dvx over dt. The reason the volume is changing over time because the change in volume of the air is also equal to the change in volume of the water inside the bottle. So dv dt is equal to v dot, which we know is equal to the cross-sectional area times the velocity times the nozzle velocity. And then just rearranging this equation itself to find nozzle velocity dvx over dt, we were able to get this expression itself. And then from here, we didn't really, to essentially solve for like the nozzle velocity over time, we used MATLAB and we employed numerical integration. So essentially, in terms of MATLAB code, it will look like, v of x of I plus 1 is equal to these expressions, which are all constant, except for we have a v of x squared term. This v of x will be v of x of I squared. So essentially, the nozzle velocity after is equal to all of these constants multiplied times nozzle velocity of I squared.